Welcome back. In our previous sessions, we mapped the AI hierarchy and explored the building blocks of tokens and embeddings. Today, we are opening the hood to look at the engine itself, the transformer architecture. This is the specific technology that made the current AI revolution possible. From sequential bottlenecks to the networked constellations powering modern AI, this session will give you a clear, structured understanding of how transformers actually work. Before 2017, AI relied on recurrent neural networks, or RNNs. These models process text sequentially, one word at a time, like reading left to right on a conveyor belt. This created three critical limitations. First, a sequential slowdown. Words had to be processed one by one, with zero capacity for parallel processing across multiple GPUs. Second, vanishing memory. The model would physically forget early context by the time it reached the end of a long sequence. And third, a distance disconnect. The model could not connect related words like agreement and signed when they were separated by several words on the belt. These limitations meant RNNs simply could not scale to the demands of modern language understanding.
Everything changed in 2017 with a landmark paper titled "Attention is All You Need," published by Vaswani and colleagues at Google. With over 170,000 citations, this paper became the foundation for GPT, Claude, and Gemini. The breakthrough was replacing sequential processing with a mechanism that processes all words simultaneously. Instead of a sequential chain where information degrades over distance, the new paradigm created a parallel attention network with simultaneous global connections and instant context. The result was training times that were 100 times faster due to massive parallelization.
So, what exactly is attention? At its core, self-attention means every word in a sentence attends to every other word in that same sentence to gain context. Consider the phrase, "the cat sat on the mat." When the model processes the word sat, it doesn't just look at neighboring words. It builds a complete attention map, a token correlation matrix, where every word is scored against every other word. The word sat attends strongly to cat, with a score of 0.9, asking, who is sitting? It gives itself a moderate self-relevance score of 0.5, and a function word like on gets a low relevance score of 0.2. The key insight is that distance no longer matters. Every word builds a new representation of itself based entirely on its contextual relationships with the rest of the sentence.
To calculate attention, each word is transformed into three distinct vectors: the query, the key, and the value. Think of it like a search engine for language. The query is what you type into the search bar. Its function is to ask, what information is this specific word seeking to understand its context? The key is like the article titles in a database. Its function is to declare, what specific information does this word hold that others might need? And the value is the actual text of the article. Its function is to deliver the core meaning and content this word will provide if it gets matched. At the bottom of the process, a query searches through the keys to find the best matches, then retrieves the corresponding values.
Now let's walk through how attention is actually calculated through vector multiplication. There are 4 steps. Step 1 is the match. The query calculates compatibility with every key using a dot product. Step 2 is the scale. We divide by the square root of the dimensions to prevent gradients from exploding and breaking the training process. Step 3 is the softmax. This converts the raw scores into clean percentages that total exactly 1.0. For example, 90% for cat and 10% for mat. And step 4 is the delivery. We multiply the percentages by the gold values to get the final, context-aware word representation. This 4-step process is known as scaled dot product attention, and it is the mathematical heart of every transformer model.
One head of attention might only focus on one type of relationship, like grammar. To capture the full complexity of language, we use multi-head attention, which runs dozens of these attention mechanisms in parallel, each applying a different lens to the same text. Consider the sentence, "The cat that chased the mouse ran away." A syntax lens identifies that cat is the subject and ran is the verb, linking them grammatically. A semantic lens sees cat as the predator and mouse as the prey, capturing meaning. And a positional lens tracks the physical distance between words, distinguishing between immediate and distant relationships. Single attention can only focus on one type of relationship at a time. Multi-head attention runs all of these parallel systems simultaneously. For scale, GPT-3 utilizes 96 distinct attention heads to capture the full nuance of human language.
Now let's look at the complete transformer architecture. The full structure consists of two main stacks, the encoder on the left and the decoder on the right. The encoder processes the input sequence. It starts with embeddings and positional encoding at the bottom, feeds into multi-head attention, passes through an add and normalize layer, which is the residual connection, and finishes with a feed-forward network. The decoder generates the output. It follows a similar pattern but includes masked multi-head attention to prevent looking ahead, an encoder-decoder attention layer where the decoder sends queries and receives keys and values from the encoder, and finally a linear and softmax layer that produces output probabilities. What was once a black box of complex mathematics is now a logical, transparent machine built on parallel search and contextual mapping.
Let's zoom in to the encoder stack. Its sole job is to process the input sequence and map it into a massive, context-rich mathematical representation. It has three core layers. Layer 1 is multi-head self-attention, where all words are input simultaneously, attending to each other to build total context. Layer 2 is add and normalize, which is the residual connection. This prevents the vanishing gradient problem, allowing for deep networks of 100 or more layers. And layer 3 is the feed-forward network, a two-layer neural network applied independently to each position, adding nonlinear expressiveness to the data. Together, these three layers transform raw token embeddings into rich, context-aware representations that capture the full meaning of the input.
Now let's look at the decoder. During training, the decoder must predict the next word without cheating. This is where the mask comes in. Masked self-attention ensures the model can only attend to words that occurred before the current position, enforcing true autoregressive generation. Think of it like a spotlight that can only illuminate text to the left. In the phrase, "I love chocolate," when the model is generating the word chocolate, it can only see I and love, never peeking ahead. This constraint is what forces the model to learn genuine next word prediction.
Cross-attention is the bridge that connects understanding to generation. It is how the decoder communicates with the encoder. The encoder processes the full input and outputs a contextual map containing magenta keys and gold values. The decoder, working on generating the output, sends cyan queries back to the encoder asking, which part of the input should I focus on right now? Consider a translation task. The decoder, writing in Spanish, sends a query to the encoder which holds the English source text, essentially asking, which English word should I focus on right now to generate the next Spanish word? This cross-attention mechanism ensures the generated output remains grounded in and faithful to the original input. Because transformers process all words at once in parallel, they have no natural sense of word order. This creates a real problem. Without sequence information, the phrases "dog bites man" and "man bites dog" look completely identical to the model, just an unordered set of the same words. The solution is positional encoding.
By adding permanent positional tags to the word embeddings using sinusoidal wave functions, the model mathematically understands the relative distance between words without relying on sequential processing. Each position gets a unique mathematical fingerprint, so the model always knows exactly where each word sits in the sequence.
So why did transformers win? Why did they become the industry standard? The diagnostic comparison between RNNs and transformers tells the story clearly. In processing style, RNNs are sequential, handling one word at a time, while transformers process all words at once in parallel. For training speed, RNNs are slow because they cannot parallelize, while transformers are extremely fast and highly parallelizable. For long-range dependencies, RNNs perform poorly due to information loss over distance, while transformers excel with direct, instantaneous connections between any two words. The trade-off comes in memory complexity. RNNs use linear memory at O of n, while transformers require quadratic memory at O of n squared, because attention requires every word to look at every other word. This quadratic cost is the current frontier of AI engineering, driving the race for million-token context windows.
You've now mastered the technical foundations of Module 1, tokens, embeddings, and the transformer engine. This is the architecture that reshaped the world. Context is everything, because word meaning is no longer static, it is dynamically calculated based on surrounding context. Space over time, because by converting sequential processing into parallel space, models can now ingest trillions of tokens. And the O of n squared frontier, because the quadratic memory cost of perfect attention is driving the race for ever larger context windows. But how do we teach these engines specific skills? In Module 2, we move into learning paradigms, exploring fine-tuning and the power of retrieval-augmented generation. I'll see you there.